Hi, I'm Mrs. Rutchling. Welcome to Chapter 17, Titration and pH Curves. A titration is simply using a solution that has a known concentration, reacting it with a solution that has unknown concentration. And then you can find the concentration of the unknown. The analyte is the solution with unknown concentration, the one we're analyzing. The titrant is the solution with the known concentration. We're looking for the point when the moles of acid are equal to the moles of base, and we usually use an endpoint of an indicator to show us this. What did one titration tell the other? Let's meet at the endpoint. pH curve is also called a titration curve, and we're plotting the pH of the analyte versus the amount of titrant added. We're going to be using millimole. It will allow us to eliminate lots of conversions each time. The relationship between millimole and milliliter is the same as between mole and liter. One way for us to find the millimoles is to take the molarity and multiply it by the milliliters. That's going to give us millimoles. You do not have to do this, but that is how I'm going to do my problems because I find it much quicker and I don't have to keep converting back from moles to molarity and then dividing by liter. Here are three different titration curves. We have a strong acid and a strong base. I know it is a strong acid because before I've added any base, the pH is even less than 1. Here I have a weak acid and a strong base. This time the pH higher, so it is a weak acid. We'll talk about how I know if it's a strong base based on the endpoint. Here we have a weak base indicated by a pH close to 11, and it is being titrated with a strong acid. Let's look first at a titration of a strong acid and a strong base. As we start, before we add any titrant, we have just our acid. I'm not showing the water molecules in this case, and that low pH tells us it's strong. As we start to go to the equivalence point, remember equivalence point is where the moles of acid equal the moles of base, our pH goes up slowly. In this case too, there are two indicators shown on this graph. The orange would change from 5 to 6, and the phenolphthalein would have a change interval here of 8 to 10. Phenolphthalein is often used in titration of acid-base. After I've added a small amount of titrant, so this area, I have spectator ions, my sodium, I have my chloride ions, and I have one hydrogen ion. What happened to the other? Because there were two, it reacted with the hydroxide that was added to create water. Notice that there aren't any hydroxide ions here. Everything added at this point has reacted with a hydrogen ion. Just before and after the equivalence point, the pH rises rapidly. When you're doing a titration, you have to add very small amounts of your titrant so that you don't overshoot it. Once we get to exactly the equivalence point, the number of moles of acid equals the number of moles of base. That means all of the acid in the base has reacted, and it only has water and the spectator ions, sodium from the base and the chloride from acid. After the equivalence point, we continue adding hydroxide, but there's nothing to react with. So the hydroxide ion number increases and also the sodium ion increases. So there are 4 points where you can calculate a strong acid, strong base titration. Before you add any titrant, it is just a pH of your initial acid. Perhaps you might be asked also to calculate the pH of the base that's being added. Before the equivalence point, the remaining hydrogen ions, those that haven't reacted with the hydroxide, hydrogen ions that are left, can be calculated, and you can calculate the pH. For a strong acid, strong base titration, the pH is 7. After the equivalence point, you can calculate the hydroxide ion concentration from the excess total volume, and then you can manipulate that to calculate the hydrogen ion concentration and the pH. We're going to look at this strong acid, strong base titration. We are starting with 50 milliliters of 0.2 molar nitrate being titrated by 0.1 molar sodium hydroxide. At this point in the titration, No sodium hydroxide has been added. It is simply a pH problem. Because the pH is only from the nitric acid, which completely dissociates, being a strong acid, the hydrogen ion concentration is the same as the molarity of the nitric acid. Taking the negative log, the pH is 0.7. Once we've started the titration, we have to take into consideration the amount of hydrogen ions that have reacted with the hydroxide. First thing to do is convert from to millimole. For sodium hydroxide, 10 milliliters times 0.1 gives us 1 millimole. 50 milliliters times 0.2 gives us 10. Plugging those values in, then you take the smallest millimole, the smallest value, and subtract both of them. That means after we've added the 10 milliliters of sodium hydroxide and it's reacted, we are left with 9 millimoles of hydrogen and all of the hydroxide has been used up. Take the number of millimoles and divide it by the volume. Remember to total both volumes to get a total volume of 60. The molarity is then 0.15 molar. Taking the negative log gives us our pH. In this problem, 20 milliliters of sodium hydroxide has been added. Again, we're starting with 10 millimoles of hydrogen. Putting those in, always subtracting the smaller value, we are left with 8 millimoles of hydrogen ions and no hydroxide. Once again, we take our 8 millimoles, divide it by the total, which is now 70, because we have added 20 and 50 together, gives us a molarity of 0.11. Taking the negative log, the pH is 0.94. We continue on, and at this point we are halfway to the equivalence point. We have added 50 milliliters. Once again, we calculate the millimoles and plug those in. Divide the 5 millimoles by 100 milliliters, the total, getting us 0.050 molar. Taking the negative log gives a pH of 1.30. Adding 100 milliliters of sodium hydroxide allows us to reach the equivalence point. As always, we've had 10 millimoles of hydrogen. At this point, neither the acid or the base is adding hydrogen ion. That means all of the hydrogen ions are coming from water. If the hydrogen ions come from water, that concentration is 1 times 10 to the negative 7, taking the negative log, giving us a pH of 7. At the equivalence point, for a strong acid and a strong base, the pH will always be 7. What happens once we pass the equivalence point? Now there's more hydroxide ion, and always remembering to subtract the smaller of the two values, we end up with 5 millimoles of hydroxide left. Dividing that by the total gives us a value of 0.25 molar. Remember that this is hydroxide, so you're going to find the POH and then take 14 minus the POH to come up with a pH of 12.40. As we look at our strong acid, strong base, adding 0.01 milliliters creates a huge jump. You can see how quickly it changes here. Makes it very difficult to do a titration, and you have to add very small amounts. At the equivalence point, the number of moles of acid equals the number of moles of base. You may use the dilution formula. The molarity of the acid times the volume equals the molarity of the base times the volume, but only if that ratio of moles of acids to moles of base is 1:1. Titration of a weak acid and a strong base, we see that the pH is a little bit higher. We have our acetic acid solution beforehand. It's a weak acid, so before we've added any titrant, it is simply a weak acid. Once hydroxide is added, it converts acetic acid or the weak acid into its conjugate base. That should sound familiar to you. A weak acid and its conjugate base creates a buffer, and we call this area a buffering region. Once we get to the equivalence point, the acid has been completely neutralized, but we still have our sodium acetate. So our acetate ion, our conjugate base, will be present. That's why our pH is higher, because our conjugate base is present. Once we've passed the equivalence point, there's no acid left to react, and we have excess hydroxide influencing the pH. Calculating the pH, when you're titrating a weak acid and a strong base is a two-step problem. Step one is stoichiometry. We assume that the hydroxide reacts completely with the weak acid. Two things have to be determined: how much of the acid is remaining and how much of the conjugate base has been formed. Using those concentrations, we do an ice chart and do an equilibrium. We can then calculate the concentration of the hydrogen ion and calculate the pH. The pH at the equivalence point of a weak acid, strong base is always greater than 7 because the anion of a weak acid is a base. The stronger that conjugate base, or the anion, the higher the pH of the equivalence point. This set of problems will be the titration of a weak acid, acetic acid, and you can see the equilibrium constant, with the same 0.1 molar sodium hydroxide. Before the titrant, or the sodium hydroxide, is added, we are doing a weak acid problem. The 50 milliliters of 0.1 molar acetic acid has been changed to millimoles. Then plug into the equilibrium expression. I have a value of 9.468 times 10 to the negative third for X, which is our hydrogen ion concentration. Because this is millimoles, divide by the milliliters to get the molarity, and I can use that to get the pH. At this point in the titration, 10 milliliters of the sodium hydroxide has been added to the 50 milliliters of the acetic acid. I know from the last problem that 50 milliliters of 0.1 molar acetic acid is going to give me 5 millimoles of acetic acid. So I don't need to recalculate that. Taking the 10 milliliters, multiplying it by 0.1 gives us 1 millimole sodium hydroxide. Anion always increases by the number of millimoles of acid that decrease. I have 4 millimoles of my acetic acid and 1 millimole of my conjugate base. Dividing each by 60, because that is the total volume, gives me the molarity for each one. I then put them in my second step to calculate the pH. I have the acid present, but I also have the anion. This part of the problem is similar to a common ion problem. Put the values in my ice chart, solve for X, which this time is the hydrogen ion concentration. Taking the negative log gives me a pH of 4.14. At this point in the titration, 25 milliliters of the sodium hydroxide has been added. Again, there are 5 millimoles of the acetic acid. This time, 2.5 millimoles of hydroxide. Taking the smallest one and subtracting, there is 2.5 millimoles of acetic acid left in the solution, and there is 2.5 millimoles of the acetate ion. Dividing both of them by the 75 milliliters, the total added so far, gives the molarity. That leads to the second part of the problem. Taking those values and plugging them into the equilibrium expression allows me to calculate the pH. This is halfway to the equivalence point. How do I know? You can look at the titration graph, but you can also look at your values. We started off with 5 millimoles of my acid, and we have reacted 2.5. So that is halfway exactly to the equivalence point. I'm going to need 5 millimoles for the complete reaction, so my 2.5 millimoles tells me that I am halfway to the equivalence point. We have equal concentrations of a weak acid and its conjugate base. That should sound familiar. That is a buffer. If the concentrations are equal, those cancel out, and my equilibrium constant is equal to my hydrogen ion concentration. Thus, at halfway to the equivalence point for a weak acid strong base reaction, the pKa is equal to the pH. You should be able to look at a graph, find this point, and calculate the pKa and eventually the Ka. At this point in the titration, 50 milliliters of sodium hydroxide and 50 milliliters of acetic acid have been added, having both 5 millimoles in each. The only thing present in our solution is 5 millimoles of acetate ion. Dividing the 5 millimoles by 100 milliliters gives us 0.5 molar. Since this sodium will not react, the acetic acid is going to react with the water to create a hydroxide ion. Putting that value, the molarity of the acetate ion, into our ice chart, we can calculate the hydroxide ion concentration. At this point, we can't use the acid dissociation constant because we have hydroxide. How do we figure out the base equilibrium constant? Knowing the relationship between the acid equilibrium constant and the base equilibrium constant, along with the water equilibrium constant, allows us to calculate our base equilibrium constant. Plugging those values in, we can solve for our hydroxide concentration. Once the hydroxide concentration is known, the pOH can be calculated and the pH can be calculated. pH of a weak acid and strong base is always greater than 7 because the conjugate base will cause solution to be basic. Continuing to add sodium hydroxide will give us more sodium hydroxide than is needed to neutralize the acetic acid. Subtracting the smallest value tells us that we have hydroxide left as well as some acetate. Because the hydroxide is going to have a bigger impact on our pH, we can ignore the acetate ion. Once again, the hydroxide concentration is calculated, the pOH is calculated, and finally the pH is calculated. Comparing titration curves. Strong acid will start with the lowest pH and have a flat part of the curve before sharply going up and then leveling off for hydroxide. As the acid becomes weaker, you can see the difference in the first part of the curve. Strong acid, strong base. At equivalent, the pH will be 7. With a weak acid and a strong base, the pH will always be above 7, halfway to equivalence point. Get the pH from the graph, calculate the pKa, and then calculate the K. The College Board likes to show you the opposite, titrating a weak base. So be aware that if you have to draw this curve or label it, the weak base has a high pH compared to where our acids were. The equivalence point is less than 7 because a weak base has a strong conjugate acid that is going to make the solution acidic, and it will drop off and become acidic as the hydrogen ions are added. Another curve to be familiar with is a polyprotic acid. There are equivalence points for each dissociation. The first is the first hydrogen, and it stops about here. We have one equivalence point, and then taking another hydrogen off, we have a second equivalence point.